Oh, actually, I have more sheets. Okay, good morning. Yesterday, we continued on in our understanding of carbonyls. We talked about tautomerization. Can someone define tautomerization again? I didn't give you exactly a definition of tautomerization, but can you define it?
Chemically interchangeable structural isomers.
Close.
Well, that's what you told us.
That's what I told you tautomer meant. Tautomers are chemically interchangeable structural isomers. So tautomerization,
Like using a base to
yeah,
convert it.
using base catalyzed tautomerization or acid catalyzed tautomerization, just our process of converting between tautomers. So if tautomers are chemically interchangeable structural isomers, and you guys appreciate why that's unique, right? Think about these structural isomers. I use these examples a lot in general chemistry. Good morning. Oh, you've got one, don't you? Yeah, you're really good at that. I use these examples in general chemistry and OChem 1 when talking about intermolecular forces. Same chemical formula, same molecular mass, just structural isomers, meaning that they've changed. Do you know how you could chemically convert pentane into neopentane? I don't. There's certainly not a simple reaction that would make and break all of the bonds that you need to chemically convert these. That would be very challenging. Most structural isomers are not chemically interchangeable. Even take, for example, the idea of an amino acid. What if instead you actually had a hydroxyamide? Those are structural isomers, but to chemically interchange them, you would have to break the carbon-oxygen and carbon-nitrogen bonds. It would be a long process and would probably involve a lot of other reagents. But this idea of carbonyls converting into their enols, where the only thing that's changing is the hydrogen. The position of the hydrogen is changing. But otherwise, the carbon-oxygen bond stays the same. It just moves from double to single. The carbon-carbon bond stays the same. It just moves from single to double. This is a unique conversion. Structural isomerism is usually not chemically interchangeable. So we've got these tautomers, and we can convert between tautomers in basic and acidic conditions, but we are predominantly going to use basic conditions. We even talked about how different types of bases, kinetic bases and thermodynamic bases, can leverage different regiochemistry of ketones. And then we introduced this idea of complete enolization. And I want to add to this a little bit more. I want to clarify some of our points here. If I make an enolate out of this aldehyde, propanal, I'm going to use just simple hydroxide, which is going to make a byproduct of water. Keep in mind, this would be just part of the tautomerization. If we stopped here, if we could isolate this enolate, how much of our sample would be enolate and how much of it would be aldehyde? We would see greater than 90% aldehyde remaining and less than 10% enolate formed. So in terms of reactivity, if I'm looking to use an enolate, and we're going to do that throughout this unit, if I'm looking to use an enolate, using a thermodynamic base doesn't have good equilibrium for my enolate. And you can see why. The alpha hydrogen has a pKa around 20, whereas water has a pKa around 16. More negative pKa, better acid. More positive pKa, worse acid, which means equilibrium actually favors the reverse direction, which is why we've got 10% to 90%. So what if I wanted to take this aldehyde and make every molecule in my sample an enolate? What do I react it with? Right. We introduce LDA. And remember, the byproduct of LDA is diisopropyl amine. pKa around 20, pKa around 35. Now we look at roughly 0% carbonyl remaining, 100% enolization. What functional group did we show this with yesterday? We showed complete enolization with which of our carbonyls? The ester. So LDA will completely enolize. Enolize. LDA will run complete enolization on ketones, on aldehydes, on esters. It's very useful for that. Okay, so with that in mind, I want to give you guys some details about these reactions before you fill in the roadmaps below. On this top left roadmap, we've got north, south, east, west. The reaction running north is acid catalyzed alpha halogenation. Notice that the halogen is added to the alpha carbon of the carbonyl. There is information about regiochemistry here. What can you learn about the regiochemistry of alpha halogenation? Wonderful. It halogenates at the more substituted position. And it does this because that more substituted enol is more stable. So we see enolization during the reaction with acid, and then we see halogenation with the elemental halogen. Why does the halogenation add at the more substituted position? Because the more substituted enol forms. Why does the more substituted enol form? That's more stable. More stable alkene is more substituted. The more stable enol is more substituted. Now I want to draw your attention to the reaction that runs north just to the right. That is also acid-catalyzed halogenation. But notice that this time it's limited on how many alpha hydrogens there are. This ketone has a benzene ring on the left, no alpha hydrogens, and a methyl group on the right. So Layla pointed out that this is regioselective. Adds the halogen to the more substituted carbon because that more substituted enolate forms. What we see in the other reaction is that when there is only one enol that can form, when there's only one position that can become halogenated, it's only halogenated once. The reason that acidic conditions will only halogenate once a halogen is added to an alpha carbon, the carbonyl becomes less basic. So in acidic conditions, adding that halogen has made the structure less reactive as it goes. In order for this first step to work, the carbonyl oxygen has to be able to act as a base so that the alpha carbon can act as an acid. Once it's been halogenated, the inductive effect from that halogen makes the oxygen less of a base, less likely to react in acidic conditions. Was this too confusing? I don't think I clarified this well. These aren't tautomers. That was clear, right? These are just other types of structural isomers that can't be chemically converted. I didn't want that to be left hanging. Okay, in our reaction to the right, we've got base catalyzed alpha halogenation. The distinction here is that a kinetic base, like LDA, is only going to react on that less substituted alpha carbon. So you see LDA going to the left, working with bromine. You see a thermodynamic base, NaOH, going to the right. Other thermodynamic bases, those are just small molecules like meth oxide, eth oxide. Those small alkoxides that work for deprotonating esters. They work with our more substituted alpha carbon. And what we can see about the base catalyzed conditions if there's multiple alpha hydrogens, then there will be multiple halogenations. On the reaction diagram that's on the top right, you can see that the methyl group is halogenated threefold, and then the methyl group is kicked off of the molecule. Okay, I need to make a small correction. The LDA here is not acting as a catalyst. That's my fault. If it were tert butoxide, it would be catalytic. If it were hydroxide or alkoxides, it would be catalytic. But LDA, remember, the conjugate acid of LDA is a very bad acid. So LDA is actually not catalyzing it. More importantly, though, what I want you guys to recognize here is that it will run multiple halogenations. And this actually gets us to that reaction that is on the right-hand side. This is given its own separate name. It's referred to as the haloform reaction. If there's a carbonyl that has a methyl group on it, a ketone or an aldehyde that has a methyl group, then we can run the haloform reaction. You guys know any haloforms? Cinema has introduced you to a haloform. You know it? No? Charades. We're doing a game of charades. What haloform am I? You don't know any haloforms? I know you know a haloform. Think of what halo can be swapped out with. Yeah. Oh, sorry. I don't know why. I forgot my M in halo form. We're talking what?
Are we talking about movies?
Yes, there's a halo form that you're introduced to because of film. Everybody knows it. Do you know iodoform? Do you know bromoform? Do you know chloroform? Oh, the big sigh. Yes, chloroform is a haloform, and the haloform reaction is what produces these. So in general, when you have this aldehyde or ketone, I've already given you one that was a ketone, so now I want to give you one that's an aldehyde. And you react this this methyl carbonyl in the presence of excess base and excess halogen. What happens is the cleavage of that methyl carbon. It is kicked off of the molecule. On your diagram, I gave you the bromoform reaction. This is the chloroform reaction. So what exactly is chloroform or bromoform? It's this small molecule. CHX3 is a haloform. The haloform reaction produces CHX3. Shall we look at the mechanism? It's really fun. What I'm going to do is draw it up on the board quick. And this reaction requires, of course, 3 equivalences of elemental chlorine, but it also requires 4 equivalences of hydroxide. So I'm going to draw each of those up on the board as I go. So 4 equivalences of hydroxide and 3 equivalences of Cl2. The Cl2 doesn't play a role right away. We're in basic conditions. So our alpha carbon is deprotonated. What is being formed in that step? You're welcome. Do you know what the name of that is? An enolate. That's the conjugate acid, that's the conjugate base of our alpha carbon, the enolate. Now that I have an enolate, I actually have a nucleophile. But because this enolate is in resonance, because the negative charge sits on both oxygen and carbon, I have to decide which atom is more nucleophilic. Which atom is more reactive with the lone pair, oxygen or carbon? Which is a better nucleophile, carbon or oxygen? Oxygen's a better nucleophile, shares its electrons more willingly. Carbon shares its electrons more willingly. Carbon is a better nucleophile. So then why am I drawing this resonance form? Because we know there's another resonance form. There's a resonance form where the negative charge is just drawn on the carbon and the double bond is still present on the carbonyl. Why am I drawing this form? It's more stable. Oxygen stabilizes the negative charge. If you want to show the other form, to show that carbon is the nucleophile, you can, but carbon is still nucleophilic from this form. Because if you remember, no resonance form truly exists. Question. Why is the alpha carbon as acidic as it is? Why is the alpha carbon even acidic? We said other types of carbons like that, sp3 carbons, are not nearly as acidic. Why is the alpha carbon so acidic? Because of the resonance with the carbonyl. So this is the major resonance form, which is why I like to draw it. Does placing a halogen on the alpha carbon make the alpha carbon more acidic or less acidic? Think of karyo. Think of which trend in karyo is changing from no halogen to one halogen. Is it more acidic or less acidic? Is there any change in charge on the alpha carbon before halogenation and after? No. Has the atom donating the hydrogen changed? It's still carbon. Is there a different amount of resonance? No. The resonance with the carbonyl is still the same, and there's no sharing to the bromine or the halogen. How about induction? Is there a difference in how electrons are being pushed or pulled? The highly electronegative halogen pulls electrons towards itself. Does that make carbon more acidic or less acidic? More acidic. If I put a negative charge onto that carbon now, meaning if I get it to act as an acid, the bromine will help pull the negative charge towards itself. So this has just become even more acidic than it was before. So if I was able to deprotonate the first time, I'm able to deprotonate even quicker this time. I make another molecule of water. I make another nucleophilic carbon. My carbon is still nucleophilic from the alpha position. And I have successfully dihalogenated my alpha carbon. Kick out a byproduct of chlorine. Is the alpha position more acidic or less acidic than it was before? More acidic. This is the most acidic the alpha hydrogens have been throughout this whole mechanism, because now there's two halogen groups on that alpha carbon. So another equivalence of base readily deprotonates and leaves us with our enolate once again. And our enolate attacks our last equivalence of chlorine. So our haloform reaction has effectively helped us produce this tri-halogenated alpha position. Great. The problem is that in highly basic conditions, the carbonyl carbon has just seen its partial positive dramatically increase, which means that the carbonyl is now very electrophilic, opens into this tetrahedral intermediate that then kicks off the haloform group. How many times have you seen a carbon-carbon bond break because one of the carbons took the electrons and left? You have not seen that very many times. We had a hard enough time getting to form carbon-carbon bonds, but getting to break a carbon-carbon bond where one of them takes the electrons, that doesn't happen often. Why did it happen? Because this methyl carbon has 3 halogen groups that can all help stabilize that negative charge. That trihalomethyl has pulled electrons with it, stabilized by the halogens, and it's now in the presence of a carboxylic acid. So if we wanted to work up this reaction, we might need to protonate our carboxylic acid, but we certainly have formed our haloform. There's some danger to this reaction. If you run this reaction unintentionally, you can make toxic amounts of chloroform. You know, that's what cinema lies to us about. It makes it seem like you can just dump chloroform onto a rag, hold it over someone's mouth, and then they pass out. But actually, the amount of chloroform you need to knock someone out is so close to the amount of chloroform that kills them. So you're more likely to kill somebody than you are get them to knock out. You can accidentally produce those toxic amounts of chloroform. If you take something like acetone, which has a methyl carbonyl, and drain cleaner, which often has sodium hydroxide, and bleach, which can produce chlorine. If you mix all of these together unintentionally, it will react and produce chloroform. Which is why you should never go into your bathroom and just dump everything that you have into the toilet, because side reactions like this happen. In fact, I've heard of students saying they found videos like this where they say what ingredients you need to get to mix together in your home toilet bowl to make these weird reactions happen. Don't do those. Don't listen to those videos. Crazy. Notice how repetitive this mechanism is. It's a lot of steps for the haloform reaction, but it's the same thing happening every single time, except for here at the end where we do the acyl substitution. All right, I gave you three things. I gave you acid-catalyzed alpha halogenation, base-catalyzed alpha halogenation, and then I've got this third reaction for you, radical alpha halogenation. What do you notice about the regiochemistry? Layla, you pointed this out earlier. What's the regiochemistry of radical halogenation? Will radical halogenation prefer a more substituted or a less substituted side? More substituted. We learned that back in OChem 1. We learned that radicals are more stable on more substituted position. Prefers a more substituted radical intermediate. All right. So we are able to substitute at our alpha position to put a halogen 3 different ways. We can control the regiochemistry, we can control the quantity, we can control, you know what, I'm not talking about stereochemistry here, but we could absolutely talk about how this controls, how this impacts chiral carbons or achiral carbons. In the second of our diagrams, down here in the bottom, we've got different alpha halogenation, or 2 different alpha substitution reactions running along the bottom. And actually, one of them is just half of the other. If you look at that starting material going to the left, it shows alpha substitution, specifically alkylation of the alpha carbon to add a methyl group. If you look on the right, it shows 2 alpha alkylation reactions sequentially. So this is our 4th type of alpha substitution, alpha alkylation. Alpha alkylation is most commonly done with those shared alpha carbonyls, a beta keto carbonyl. So you see there that we've got ethyl acetoacetate going through its alpha alkylations. I want to show you guys what this looks like. So let's take the reaction that goes to the right. First, we introduce ethoxide. It's important that we don't introduce meth oxide or hydroxide. The reason it's important that we use ethoxide, we want this base to match the ester linkage so that we don't do any trans esterification and we don't hydrolyze the ester. So we're using a base that matches. Ethoxide deprotonates and gives us an enolate. This is one good resonance form. There is a different good resonance form for this intermediate. Do you guys see how the enolate could have formed with the carbonyl on the left? Either one would be perfectly acceptable. They're both major resonance forms. They're both a lot like what the molecule looks like. Then we introduce our electrophile. In this case, I was using methyl iodide. Methyl iodide is my electrophile. What is my nucleophile? Perfect. It's not just the enolate, it's the alpha carbon of the enolate. And how did you know that the alpha carbon was the nucleophile? Well, look at this mechanism for haloform. Nucleophile, nucleophile, nucleophile. The alpha carbon has always been the nucleophile. Now, if I wanted to do the mechanism for the next alpha halogenation, or excuse me, alpha alkylation, I would need to deprotonate that second alpha hydrogen. Which is more acidic? The hydrogen that we eliminated first, call it hydrogen A, or the hydrogen that we eliminate second, call it hydrogen B. Which is more acidic? Why?
It's more substituted.
Layla, do you agree?
I'm going to say induction.
What has changed about the induction? A push or a pull? I agree. Methyl pushes electron density as opposed to halogens, which pull electron density. Pulling is better for an acid. Pushing is better for a base. So actually, we'd say induction might make it feel like it's making it less acidic, but the substitution means the enolate is more substituted, and that has a bigger impact here. Do you guys want to see the next substitution mechanism? You're okay with recognizing that it's exactly the same deprotonate nucleophilic attack? Well, since you're okay with it, then I'm just going to show it. And you can have your choice on whether you want to write it down or not. This time I've decided to show my resonance form going to the other carbonyl because I have every choice to. And for that second alkylation, I decided to show ethyl bromide. Oh, that's funny. I usually give like some sort of halogen or a phenyl-containing group. Nucleophile attacks from the alpha carbon, substitutes the halogen, and leaves me with my dialkylated carbonyl. You guys are okay with the halo form mechanism if I clear that? Anybody want a picture of it? Okay. Good question. No. Actually, none of these mechanisms will be on the test. The mechanisms, we do have a mechanisms worksheet. So the mechanisms that you're expected to know for the test, we'll go over them. We've got a worksheet for them. Actually, that's a really good way to know. If I've given you a worksheet that has a mechanism, then I want you to know that mechanism. If I have not given you a mechanism on a worksheet, then that mechanism is not as important. Okay, there's one last reaction here, but I hate to say it, it's not alpha substitution. So this is something that we will commonly see with alpha alkylation. So I'm going to keep this under the alpha alkylation header. You can see actually from the diagram, it doesn't need to be done with alpha alkylation, but it's just most commonly done with alpha alkylation. This is decarboxylation. Decarboxylation occurs when you have a beta carbonyl acid and you heat it. Well, what we were using for our alpha alkylation was not an acid, it was a beta keto ester. So we would have to first hydrolyze the ester into an acid, and then we can decarboxylate it. And I'd love to show you guys the mechanism for this as well. What happens first is that the heat drives the structure into this high energy conformation. It takes the beta carbonyl. Do you see how it makes kind of this pseudo six-membered ring? Kind of looks like a six-membered ring, except the oxygen and the hydrogen are not actually bonded. The acid will line up relative to the beta carbonyl such that its acidic proton is close to the hydrogen, close to the oxygen of the beta carbonyl. And then just from heat, no reagents necessary here, just from heat, the other carbonyl deprotonates, allowing a second CO double bond to form. That second CO double bond means that the acid carbon has too many electrons, so it needs to break a bond over to the beta carbonyl. Isn't that a fun little circle? We form an enol and carbon dioxide. We have decarboxylated. We got rid of that carbon dioxide. And then we see a preferential tautomerization back to the carbonyl. So here's what I want you guys to do. I want you to take the final product that we formed from the dialkylation. I want you to show me what it would look like if it is hydrolyzed and decarboxylated. Pay attention to what happens in the example given. Acetoacetic acid becomes acetone and carbon dioxide. And then follow that pattern. What carbons remain? What carbons are lost? Follow that pattern and predict the structure after decarboxylation. maybe map your carbons. Mapping your carbons can mean knowing which carbon is lost by decarboxylation and how long your final product chain will be. This has got everybody. Everybody's stumped. If you think about the usefulness, by the way, this is a very acidic position, so it makes it easy to make a nucleophile out of that carbon, which means we can diversify the carbon chain. We can create whatever carbon chain we want coming off of this alpha position, and then with decarboxylation, we can remove one of the carbonyls and be left with just one other carbonyl. So there's a value to being able to create your carbon chain and then cleave off an extra carbonyl that it may have. Brenna, you've got one of these, right? Okay. Mm-hmm. I know. Can I show you how I'll map it? Here's that example that you're given on the worksheet. If we map this as carbon 4 is the acid carbon, then what we notice in the final product is that carbon 4 is lost as carbon dioxide, and the rest of the chain stays as it is. So if you map your carbons, you might be able to more easily predict what the final structure should be. Mm-hmm. That's it. Notice how you still have 2 carbonyls.
Yeah, I'm working it out.
Okay.
By waiting for you.
In our decarboxylation, you should lose one of those carbons. Yes. That's it. Your carbon chains have shifted a bit. So you see how you've got a quaternary carbon?
Yeah.
And it is going to become tertiary, but now you have no tertiary carbons. Try mapping. Yeah, you did. 1, 2, 3, 4. Off of 3.
Yeah, because this will break. Oh. But I guess like the bonds.
Off of 3 comes a methyl and ethyl. So find 3 and then add those groups. There you go. Now we're mapping with fire. You're getting close. Don't feel that you need to do the mechanism every time. Find the pattern that helps you make the prediction faster. Because you know it takes time on the test to try and push the mechanism so that you can find the product. Yeah, that's it, Layla. Are you mapping? Have you mapped your carbons? If it helps to show the mechanism, work it out. Or maybe even get yourself to the hydrolyzed form so that you can map it out faster. I'm going to do the same thing again. I'm just going to start from the left and go to the right. That's exactly the same mapping that I had before. Here's what I'm going to do with my mapping this time. I'm not going to map every single carbon. What I'm going to do instead is say, off of carbon 3 is a methyl group and an ethyl group. So when I get to my final product, carbon 3 better have a methyl and an ethyl coming off of it. I'm going to do decarboxylation. I can't lose the carbonyl on the left because the carbonyl here is a ketone and it's the acid Doesn't matter what the other carbonyl is, but the acid is lost by decarboxylation. So I'm going to lose carbon 4. Do you know the easiest way to predict this structure, the product, would be to just redraw the starting material, but not have group 4 coming off. It just looks ugly. I think we can agree. So I'm going to do it differently instead. I'm going to number my carbons again, 1, 2, 3, and then recognize that off of 3, there needs to be a methyl group and an ethyl group. Mapping your carbons can save you a lot of times, right? As long as you know which carbon needs to be lost in the synthesis. Okay, fill in that roadmap. I don't like that I didn't say roadmap. Put it to work. Fill in that roadmap, and if we can be done with that in the next 15 minutes, we'll move on to our next worksheet afterwards. This is the enol form of your product. Yes. But it will tautomerize preferentially to form the carbonyl. Yep. Oh, and by the way, it doesn't matter how you draw your ethyl and methyl chain. I drew it this way, but I could have just as easily drawn it this way. Those are the same molecule. Those are just different conformations. Did I remind you guys that delta means heat? Is that something you remembered? I'd accept either one on an answer. Jordan, when you get a minute, do you want to check that the next one is already on Canvas? I believe that it is. This one's for you, Evan. No, I got it. Go. Here's our next one. Mm-hmm. You're welcome. Aldol. Oh, okay. No, I think it's probably not a refresh issue. It's probably a me issue. Yeah.
The one at the very bottom on the right,
Yeah.
when it gets hydrolyzed, do both sides get hydrolyzed?
Yes.
Okay, that's tricky.
Oh, did I miss something down there? I missed
Oh yeah, you missed
the new alpha group. Yes, both sides get hydrolyzed, but you follow the same structural prediction process. Only one of them can be lost. Just if you look in the blue mechanism up there, would you agree that it doesn't matter if the carbonyl on the left is also a carboxylic acid, is an ester, is a ketone, is an aldehyde? Do you guys all see how this position 1 played 0 role in the mechanism, in the decarboxylation? So if this is a second acid, if this is an ester, if this is an aldehyde, it doesn't matter. It's the CO double bond that allows for the decarboxylation to occur. Good question. Okay, thank you for checking for that, Jordan. I got it updated, addition and condensation.
Thank you.
Yes, you're welcome. What questions can I answer? Do. Are you looking for what finishes this? It won't be Cl2 alone. It needs to have something else.
I haven't watched yesterday's thing.
Oh, it was all from today actually, but it would all be up from here, because these are all.
So it needs
Yeah, although not actually a workup. A workup would be 1, 2.
right.
A workup would be what you do after your reaction's done. This is just a catalyst.
Gotcha.
Good, that's great. You could have also done HNu,
Right.
and it would do that, but obviously you don't want to use sodium hydroxide.
So am I using an old?
Mm-hmm.
Okay.
Yeah.
Gotcha.
I like to sprinkle them in so you can't forget them.
Maybe I'll try.
I'm sure you'll try.
Do we just use?
Great.
Okay.
I didn't actually realize the reaction I went through in class was the one I put on the sheet. That wasn't intentional. Great job on your structures. You got it. Oh, it's actually not tert butyl. It's isobutyl. So if you call it IBU,
That's fine.
yeah. But tert butyl would have the iodine coming off of that tertiary carbon.
Okay, but this
Mm-hmm.
will
That's.
come off like here.
Mm-hmm.
Okay.
So you remember isopropyl is just this, and then isobutyl just has an extra carbon chain going to it. Just a small little letter makes all that difference, huh? I, CH2, CH, CH2. Perfect. That's a great way of writing it. Are you a fan of the condensed structure?
It's just easy, unless I can draw it with lines, then.
Which you can.
Yeah, it just looks kind of ugly with the eyes. So,
Fair. This can't be an ester after the hydrolysis.
oh. Wait, what?
Yeah, the difference here is
Oh, I thought.
acetoacetate versus malonic ester. And the difference is one has a ketone, one has two esters. So your carbon chain was right. It's just the functionality.
Right, okay.
Good. Yes, but no. So here's our nucleophilic carbon. And then we want 1, 2, 3 carbons being added in. You've actually got 1, 2, 3 carbons. I want it to bond nucleophilic alpha carbon to bond to a CH2. So if you, can you copy and paste this?
Yeah.
If you take the structure that you want and then erase everything that you already have, which it's going to erase more than I meant to, but I'll try if I can. Oops. This is what we want. Those are the new carbons, the 3 new carbons. And I want something to leave off of this. Yours is a structural isomer. You agree? Same number of carbons, same groups, but the halogen is connected at the wrong spot. So if we're mapping and we say 1, 2, 3, 4, I want a reagent that has 2, 3, 4, and I want something to leave off of carbon 2. Okay, good work. You were 50% of the way there. This is good. That's the carbon chain, but both esters will get hydrolyzed in the acid, so you won't be left with an ester unless you went back and did esterification. In our example model, we were left with a ketone because the carbonyl on the left was a ketone. But here, the carbonyl that we'd be left with is an ester, but we know that esters hydrolyze in acid. Making sense?
Sure.
So do you know what change to make down there?
So it's a little funky, but if I did this, I can
Yes,
form that.
yes.
And then for this one, if I do, like, if I run the experiment, would it turn both of these into?
Mm-hmm.
Okay.
It will.
Like both sides?
Both sides. I'll come back because I'm curious about what change you make. Did I sign you off? Is that just an H? Oh no, that's an I. I'm sorry.
No worries.
Is that enough carbons? So you've already mapped 1, 2, 3, and 2 is going to be the nucleophile. So we could call those 4, 5, 6. 2 needs to bond to 4, 4 to 5. I don't think there's enough carbons. See if you can map more so that you can make sense of what structure to provide. Did you make a change yet, Jaylee? No? Let's go through some of these together, shall we? This was a review. Got to keep you on your toes. Can't let you think that it's always going to be on the sheet that you're looking at. So what's a good way to take ethanol and make acetaldehyde? Yeah, pyridinium chlorochromate. It's pretty much the only way that we have to do that. Then, how can I do mono alpha halogenation? Well, there's actually two ways. I didn't maybe clarify that enough. The radical halogenation will do monohalogenation, or acid catalyzed. So Br2 with acid, or you could have done it with light instead. Yeah, I did mean Cl2. Thank you. Now, Evan, I noticed on your sheet that you showed monohalogenation here as well, right? What we know about sodium hydroxide with our methyl carbonyls is that the first time it works to halogenate it, it makes the alpha position more acidic. So then it keeps halogenating until that methyl group is totally halogenated, and then it gets cleaved off from the structure. So the molecule that I was expecting here was actually the one that we did earlier, acetaldehyde to formate and chloroform. It's that haloform reaction. How do you recognize that it's a haloform reaction? It's basic conditions with halogens and a methyl carbon. It can't work unless there's a methyl carbon. All right, on the right, we do alpha alkylation. Now, I'm going to map these carbons. I'm actually not going to map all 3 carbonyls. I'm just going to start at 1 carbonyl, map to the alpha carbon, and then map from there. So my alpha carbon needs to bond to this new group. All right, I'm going to call that group 3,4,5. I need carbon 2 to bond to carbon 3, which means I need a leaving group on carbon 3. So I'll introduce a reagent that has carbons 3, 4, 5, and has a leaving group on carbon 3. Now, I agree that doesn't really look super legible, so I'm going to rewrite this one. I also need a step that creates my nucleophile. So the correct answer here is first put in a base. Can I use OET minus? Can I use eth oxide? Why not?
Because it's not the same linkage.
I need the base to match the ester linkage. A lot of students don't quite understand what that means. Do you all understand what that means? What is the ester linkage? Evan, could I have you try and answer it? What is the ester linkage? Yeah, or methoxy, because it's that oxygen to the methyl. So I need a base that matches that methoxy linkage. So OMe, OCH3 minus. I can use OET minus when my base is an ethyl, when my ester is an ethyl ester. But here I've got a methyl ester. Then introduce 3, 4, 5 with a good leaving group. Okay, going down below, it's the exact same thing. First, I need a base that matches my ester linkage. Once again, if I'm mapping my carbons, I'm looking for this group 3, 4, 5, and I want a leaving group off of 3. Here's 3, 4, 5, and any leaving group off of 3 works. I'm going to do it again up here in a good color. That's too many. Jordan approached this one knowing that this structure had a common name and named this one isobutyl iodide, which is good. You can call it that if you know. Well, initially you called it tert-butyl, TBU. So if you know the correct abbreviation, you can absolutely abbreviate it that way. Some of the others reported it like this in the condensed molecular formula, a leaving group attached to a CH2, to a CH, to two CH3s. I saw the same for this one up here. We can write its condensed molecular formula. You know, this is what Layla did for this one, and honestly, it's challenging for me to do that. Or at the very least, it's challenging for me to interpret this condensed structure. Unless you are exposed to it a lot, I don't look at that structure and think, there's an alkene. I don't look at that condensed molecular form and say, there's a double bond between two of those carbons. It's just not obvious to me. I just see letters and numbers. So the structures, in my opinion, are easier. You've got it. All you have to do is erase everything else and then put a leaving group on it. But there's absolutely nothing wrong with these condensed molecular forms or their IUPAC abbreviations. All right, easy enough. Let's look at our next worksheet. Oh, no, you have to sit there and not know forever. Okay, last time, the hydrolysis only hydrolyzed the ester of ethyl acetoacetate because it wouldn't hydrolyze the ketone. Ketones can't be hydrolyzed into carbonyls, carboxylic acids. Here, I have malonic ester, which means both esters get hydrolyzed to a carboxylic acid. Notice that the difference between malonic ester and ethyl acetoacetate is just that there would be a second carboxylic acid on the left-hand side here. If this were a carboxylic acid, it doesn't change anything about this step or this step or this step. The carboxylic acid on the other side would stay exactly the same. What this decarboxylation requires is that a carboxylic acid has a carbonyl beta to it. Whatever that carbonyl is fine. So the exact same process that you guys did last time. There's carbon 1, 2, 3, 4, 5, except carbon 1, which was part of an ester, has been hydrolyzed. Does that make sense? Hydrolysis of the ester to the carboxylic acid. And when the other carboxylic acid gets cleaved, notice that it's gone. 2 is no longer connected to that other carbonyl. When that other carboxylic acid gets cleaved, I'm still left with 1 carboxylic acid. Here's what I kind of enjoy about these reactions. By the way, same product, different conformation. What I like about these is when I introduce to you the hydrolysis and decarboxylation of ethyl acetoacetate, makes sense. Hydrolysis cleaves and just leaves everything as it is or creates a ketone. And then when I make the smallest modification, some of that pattern sticks and the critical thinking falls into the gaps, right? How do esters respond to hydrolysis? They hydrolyze. How do esters respond to acidic conditions? They hydrolyze into carboxylic acids. So it's a balancing game, a lot going on. Got to be able to make predictions about the structure and the functionality. You got a question?
No. I mean, I can ask it, but I figured it out.
Let's hear it.
I was going to ask why doesn't the other carboxylic acid turn to protein oxide?
Yeah. Why doesn't it?
Not the other carbonyl for it.
Yeah, because by the time one of them has been decarboxylated, the one that remains doesn't have a beta carbonyl. Would it have mattered whether I showed the carbonyl on the left being lost or the carbonyl on the right being lost? No, it wouldn't have mattered because they're identical to each other. Malonic ester is symmetric. Would it matter when I was working with ethyl acetoacetate? Yes, it matters with ethyl acetoacetate which carbonyl is lost. only the carboxylic acid carbon can be lost. The ketone can't go through decarboxylation. The ketone can facilitate decarboxylation, but the ketone itself can't be cleaved. All right. Our next worksheet takes us through what's referred to as carbonyl addition and condensation reactions. The first class is referred to as aldol addition and aldol condensation. So before we talk about it, let's talk about what aldol is trying to say. This sounds like a guy's name, doesn't it? And it's not. It's actually not named after somebody. Instead, it's a composite of aldehyde with alcohol. So the aldol reactions involve in some way this aldehyde and alcohol. The aldol reactions, there's two types, aldol addition and aldol condensation. An aldol addition reaction. It requires two things. It requires a nucleophilic carbonyl remember, that's an enolate. It requires a nucleophilic carbonyl, and it requires an electrophilic carbonyl. Well, lucky us, an electrophilic carbonyl is just a carbonyl. Carbonyls are electrophilic already. The process of taking a nucleophilic carbonyl and an electrophilic carbonyl is that they will add together to give us an aldol addition product. Now, to be fair, it doesn't actually matter whether the carbonyl is an aldehyde or a ketone. But imagine that this R group is a hydrogen. That means that I have both an aldehyde and an alcohol. So it's an aldol addition product. What's another name for that functional group? Remember yesterday I introduced some new functional groups to you. What functional group do I want you to identify that as? Electrophilic carbonyl plus a nucleophilic carbonyl react to form what functional group? Keep it generic. Carbonyl. Beta hydroxycarbonyl. That's the aldol. Can you see why it's addition? We're taking one of the carbonyl groups and we are opening the carbonyl. We're doing acyl addition. Alpha carbon acts as a nucleophile to do acyl addition on the carbonyl. The aldol elimination, well, actually, before I am. I'm going to keep going. The aldol, not elimination, the aldol condensation also requires a nucleophilic carbonyl and an electrophilic carbonyl. But the aldol condensation will take this a step further after the formation of the aldol addition product, it will go through an elimination reaction. Where it condenses a small molecule. This reaction produces water, and that's part of why they call it a condensation. The two reactants come together and condense a molecule as a byproduct. To be fair, there are a lot of other reactions that we could call condensations because of that, but we don't. In the aldol condensation, the aldol addition is just an intermediate. In acidic conditions, you cannot isolate the aldol addition intermediate. So notice on this example how two equivalences of the carbonyl react in acid and give that condensation product. Basic conditions can be controlled. You can drive it all the way to condensation. You can limit it at addition. And I'm sorry, I skipped over it. What is the functional group of our aldol condensation product? Yep. Alpha beta unsaturated carbonyl. What's the other name for this? I want you guys to be familiar with both. Conjugated carbonyl. Now, in predicting aldol addition and aldol condensation products, I find that it's easy to line up the two molecules that you have to make the prediction about their structure. So for example, I've given you acetaldehyde, two equivalences of acetaldehyde. One equivalence will serve as the nucleophile. Remember that the enolate only forms to about 10% of the sample. So when you create this nucleophile, you've got a 1:9 ratio of nucleophilic and electrophilic carbonyl. So one of these will become the nucleophile, and the other will become the electrophile. So in predicting the aldol addition, we make this bond between alpha and beta, and then we break the double bond to make an alcohol. Beta was a carbonyl carbon. I've begun to call this Ochem lore. Can you believe the beta was a carbonyl carbon? It used to be a carbonyl carbon of its own right, and now it's a beta carbon. That's what happens when you get taken over by alphas, become beta. Isn't that like literally, that's the alphabet, that's the way it goes. Okay, so there's my carbonyl carbon. And if I wanted to do this again to predict the aldol elimination, sorry, I don't know why, I've never called it that before in my life. The aldol condensation, here's my alpha carbon, here's my beta carbon. The difference this time is that both of the bonds to the carbonyl get removed. Another way that I like to make this prediction for the condensation product is I'll line up alpha above the carbonyl, and then I'll just reuse. No, I did something wrong there, didn't I? Oh yeah, no, that's alpha. I'll just kind of combine them. I can see that that doesn't read very pretty. Alpha attacks beta. Beta was a carbonyl carbon. So when you make an alpha beta unsaturated carbonyl, you are just taking the carbonyl beta and making sure it's no longer a carbonyl. Okay, that's the aldol addition, and it doesn't need to be with an aldehyde, which is why I've shown you how it works with a ketone. And with the ketone, what I've decided to remind you about is the regiochemistry. When you do aldol reactions with a ketone, especially a ketone that has different degrees of substitution on either side, the thermodynamic base forms the thermodynamic enolate, attacks from the more substituted carbon. When you use a kinetic base, it forms the kinetic enolate, and it attacks from the less substituted carbon. So we can control our regiochemistry. The last thing that we're going to talk about today, and we'll pick up with the rest of this tomorrow, is the crossed aldol reaction. What this means is working with two different types of carbonyl. So if I take acetone and react it with acetaldehyde in these conditions for aldol addition or aldol condensation, I want you to label the acetone as A, and then label acetaldehyde as B. And as you look at those possible products, I want you to assign them as A attacks A, or A attacks B, B attacks A, or B attacks B. Remember, you've got a nucleophile and an electrophile. So for each of these, can we identify what compound is serving as the nucleophile, what compound is serving as the electrophile? Go ahead whenever you're ready. In the first row. By the way, the first row, each row, is just the aldol addition and condensation products from the same combination of nucleophile and electrophile. This is going to be a useful tip, that the beta carbon in the product was a carbonyl carbon, and the beta carbon is the electrophile. The beta carbon comes from the electrophile. So tell me, in the first row, which reagent is serving as a nucleophile? Which is the electrophile? The aldehyde is not the nucleophile, because the nucleophile retains its carbonyl character after bonding from its alpha carbon. And in the top row, I don't have an aldehyde, do I? the top row actually gives me a ketone, which means the ketone is preserved. The ketone was the nucleophile. If you look at the beta carbon, would you agree that that's a secondary alcohol and a secondary alpha beta unsaturated? The beta carbon is only bonded to methyl and the new alpha carbon. Well, alpha attacks beta, which means that beta originally was only bonded to methyl. So in the first set of products, A has become the nucleophile to attack B. What about the second row? Is the nucleophile the same or different? Nucleophile is the same. And I can tell the nucleophile is the same because the structure around the carbonyl and alpha is all the same. So my nucleophile is still A. Is the electrophile the same in that second row? Wouldn't you agree that there's an additional methyl group? And if beta was the carbonyl carbon, then I should be able to just cut off alpha and see the structure of my carbonyl. What is that carbonyl? What's the electrophile in the second row? Is it A or B? A. So the second row shows that if A becomes the nucleophile, it might attack B, it might attack A. This is the issue with the crossed Aldol reaction, is that both reagents have the potential of being the nucleophile and the electrophile. What's the nucleophile in the last two rows? Compound B is the nucleophile in the last two rows. What are the electrophiles? In the third row, B attacks B. And in the last row, B attacks A. If you can't see it, what I want you to do is try taking the products, take the 8 products that are shown, and disconnect them, retrosynthesize them, show the carbonyl versions, show the carbonyl precursors to these 8 products. Okay, so the limitation with the aldol addition and the aldol, the limitation with crossed aldol is that we can get a mixture of products. We're not always looking to get a mixture of products. We want to maximize one product. So we have 3 things that we can do. We can limit alpha hydrogen possibilities. So you can see here that I've taken cyclohexanone and tert-butyl ketone. Tert-butyl ketone has no alpha hydrogens. Tert-butyl ketone cannot be a nucleophile. Cannot be a nucleophile. So it's only the electrophile. What about cyclohexanone? Can cyclohexanone be a nucleophile? Yes, it's got those alpha hydrogens. Can cyclohexanone be an electrophile? It can, which means that cyclohexanone can attack tert-butyl ketone, but it means cyclohexanone might also attack itself. So limiting the alpha hydrogens doesn't minimize side products, or it doesn't make it a 0, but it does make fewer. Okay, we'll talk more about the other 2 tomorrow. We can make one carbonyl more reactive than the other, or best case, most useful in synthesis, just complete enolization. Take one of them and just turn it into the nucleophile completely, rather than banking on this idea that some 10% of these are going to become nucleophilic. Just take a compound you want to be the nucleophile, make it a nucleophile, and then introduce the electrophile. Okay, we'll keep going with this tomorrow. And I have a goal of doing the mechanisms with you tomorrow since it's our last day together. Okay, if I won't see you, good luck on your final. And I'll be grading. I'll still be grading some stuff for you guys. Reach out with any questions you've got. See you tomorrow. Yeah, why'd I have to do that?